After successfully downloading the movement CLI in the upcoming videos, we will dive into the core principles of the Move language. You will learn the essential syntax, explore key data structures, and start mastering the fundamental concepts of the Move language. Just like other languages, we will explore data types in Move. First up is integer. In the previous video, we mentioned that in Move, integers are always non-negative, and there are 6 types: U8, U16, U32, U64, U128, and U256. Operations are only allowed between the same data types. You can easily perform typecasting to execute operations, but it is important to cast from smaller types to larger types to avoid data overflow. As shown in this code, adding 2 different data types will result in a compilation error. To make this expression correct, you need to use 2 identical data types. We will convert one of the data types to match the other. One thing to note when performing typecasting is that we should only cast smaller types to larger types and not the other way around. This helps to limit the risk of overflow. We will run the code to get a better overview. The code defines a module in the Move language that includes the function plus 2 types, which converts x from the U8 data type to U64 to perform the calculation. It also uses the test plus 2 types function to verify whether the calculation is valid. We will run the code to get a better overview. Follow my step on the screen here. We will use movement move test filter module to test the module, where the module in this case is integer module. It will cause an error due to a data type mismatch. The next data type is Boolean. Boolean types in Move are a primitive data type that represent 2 possible values, true and false. They are essential for implementing logic in your programs, allowing you to control the flow of execution based on conditions. We will run an example on how to declare, use, and test Boolean types in Move. This way it has succeeded. Address is an integrated data type in Move used to represent locations in global storage. An address value is a 256-bit identifier. At a specific address, 2 things can be stored: a module and a resource. Although an address is a 256-bit integer, Move addresses are designed to be intentionally opaque. They cannot be derived from integers, do not support arithmetic operations, and cannot be altered. While there may be interesting programs utilizing such features, for example, pointer operators in C serve a similar role, Move does not allow such dynamic behavior as it is designed from the ground up to support static verification. You can use address values at runtime, address type values, to access resources at that address. You cannot access modules at runtime through address values. Following is the syntax address. To distinguish when an address is being used in the context of an expression or not, the syntax for using an address varies depending on the context in which it is used. When an address is used as an expression, it must be prefixed by the character ARD. Outside of expression contexts, an address can be written without the prefix arrow. This is an example of how to declare address variables, and we can see that addresses have 2 forms, named or numerical. The next data type is signer. Signer is a data type that represents the authority and control over a resource or asset on the blockchain. The signer data type is used to designate which account or entity is responsible for executing a specific transaction or operation on the blockchain. This is an example of how to declare a signer variable. The package signer in the standard library module provides two utility functions for signer. The address of function returns the actual address associated with the signer, whereas the borrow address function provides a reference to that address for use in reference-based operations. Next, we will run the code to get a better understanding. This code demonstrates how to use a signer to create a resource and store it in the global storage at the owner's address. It also prints the signer and its address for verification purposes. We will run the test command to verify the code. It has been successfully executed. Next, we will learn about vectors. First is the overview. Vector T is the only collection type provided by Move. A vector is a homogeneous collection of T values that can be expanded or shrunk by adding or removing values from its end. A vector T can be initialized with any data type as T. Here are some examples. Vector U8, vector address. Next, we will explore operations on vectors, starting with adding a value to a vector. The following code demonstrates how to add a value to the end of a vector in Move. The function addLastVec takes a U64 number as input and returns a vector U64. It creates an empty vector using vector empty U64. The vector.pushback function is used to add the input number to the end of the vector. The test addLastVec function demonstrates how to use this function and print the resulting vector. This example showcases basic vector operations in Move, including creation, adding elements, and returning a vector from a function. This is a success. Next is get value in vector by index. The following code demonstrates how to retrieve a value from a vector by its index in Move. The function get_value_by_index_back takes AU64 index as input and returns AU64 value. It creates a vector and populates it with three values, 10, 20, and 30. The vector borrow function is used to access the element at the specified index. The asterisk operator dereferences the borrowed value. The test_get_value_by_index_back function demonstrates how to use this function to retrieve and print a value from the vector. Next is take last value from vector. The following code demonstrates how to remove and return the last value from a vector in Move. The function takeLastValue in vec creates a vector with three elements, 10, 20, and 30. It uses vector pop_back to remove and return the last element from the vector. The function returns a tuple containing the modified vector and the removed value. The test takeLastValue in vec function shows how to use this function and print both the resulting vector and the removed value. Next is an example of code for destroying a vector. Some behaviors of vector t depend on the capabilities of the element type t. For instance, vectors containing elements that can't be dropped can't be implicitly discarded like v in the example above. Instead, they must be explicitly destroyed using vector, destroy empty. Note: vector, destroy empty will trigger a runtime error if the vector is empty. Let's take a look at the example code. Function add_last_vec creates a vector and adds a drop vector element containing the value number to the end of the vector. Test the functionality of add_last_vec by adding an element to a vector and printing its contents to the console. Test the case of destroying a vector with elements without emptying it first. Demonstrates the error when attempting to use vector, destroy empty on a non-empty vector. Test the functionality of test success drop vector, destroying a vector after all its elements have been removed. The vector is emptied using vector, pop back, then successfully destroyed with vector, destroy empty. We will test the code. This way, we have successfully tested the code. Next is the final method, copying a vector. First, we must ensure that drop vector has the copy attribute, otherwise it will cause an error. Additionally, we need a test clone vector function to test the ability to copy a vector. And those are the methods of vector. Next, we will explore string. In Move, string is not a native data type. Data in the Move VM is stored as bytes, so when using a string, the essence of the string will be a vector, a sequence of characters encoded as bytes arranged adjacently to create a string. Having a deep understanding of these data types is absolutely essential for effective programming in Move. They serve as the foundational building blocks upon which numerous complex data structures and sophisticated algorithms are constructed. By mastering these fundamental concepts, developers can gain the ability to design more efficient, scalable, and reliable programs. Furthermore, such knowledge not only enhances problem-solving capabilities, but also empowers programmers to navigate and implement advanced features of the Move programming language with greater confidence and precision.